Hello, everyone, and welcome. Today, we're going to explore a fascinating topic, Unit 13, which focuses on information and communication technology. This presentation will give you an overview of how technology is shaping the way we communicate and share information. We'll cover key concepts, recent developments, and the impact of ICT on our daily lives. I'm excited to take you through this journey, so let's get started. When we think, see, hear, touch, or taste, we are gathering information about the world around us. This information is what we call data. Now, when we collect and organize this data, it becomes what we know as information. Communication is the process of sharing this information with others, whether through speaking, writing, or other means. In today's world, we often use modern technologies and tools to transfer information quickly and efficiently. This entire system is what we refer to as information and communication technologies, or ICT for short. Some common devices that help us with this include laptops, computers, mobiles, ground stations, satellites, dish TVs, radios, fax machines, telephones, and the internet. These are all examples of ICT tools. They work by using signals to send data from one place to another, making communication faster and more accessible than ever before. Understanding these concepts is essential because they form the foundation of how we connect and share information in our digital age. Signals are essentially physical quantities that change over time, and they are everywhere around us. They can be electrical signals, like the ones in our circuits, or radio waves used for communication. Light waves, which allow us to see, are also a type of signal. Temperature and pressure changes are signals too, since they vary and can be measured. Now, when we look at signals, we generally divide them into two main groups, analog signals and digital signals. These two types are fundamental in understanding how information is transmitted and processed in various systems. Let's focus first on analog signals. These are continuous signals that can take on any value within a range, kind of like a smooth wave that varies over time. They are very good at representing real-world phenomena because of this continuous nature. On the other hand, we have digital signals. These are discrete signals, meaning they have specific, separate values, usually represented as binary zeros and ones. Digital signals are the backbone of modern electronics, offering advantages like noise resistance and easier processing. Understanding these two types of signals is crucial because it helps us choose the right method for transmitting information, depending on the application. As we explore further, you'll see how each type has its unique strengths and challenges in communication systems. Let's talk about analog signals. These signals include things like sound waves, light waves, infrared radiation, radio waves, electricity, and even the movement of clock hands. They are characterized by changing continuously over time, which means they can represent physical quantities that also change smoothly without breaks. Because of this continuous nature, analog signals cannot be simply represented by binary digits like zeros and ones. This makes sense because digital systems rely on discrete values. As a consequence, analog signals can't be easily coded or compressed, which means that during transmission, there's a higher chance that the quality of the data might degrade. Another important point is that analog signals cannot be stored directly in digital storage devices. To work with them in modern electronic systems, we use devices called analog-to-digital converters. These devices transform the continuous analog signals into digital signals, enabling us to process and store them efficiently, like in microphones, for example. Understanding these points helps us see why digital systems often prefer to work with digital signals, even though analog signals are still very common in the physical world. A sine wave represents analog signals, which are continuous in both time and amplitude. This means that unlike digital signals, which are discrete, analog signals can take on any value within a range. The sine wave is a fundamental concept because it perfectly illustrates how many natural phenomena, like sound, light, and radio waves, behave. When we look at this wave, we see a smooth, repetitive oscillation that repeats over time, capturing the essence of how these signals vary continuously. Understanding sine waves helps us grasp how analog signals carry information, and it's essential as we move toward discussing how these signals are transmitted and processed in different systems. This connection is at the heart of our overall theme: how signals communicate and how we can manipulate them effectively. Now, let's talk about digital signals. These are created by devices like mobile phones, computers, and even digital thermometers, along with audio and video files and digital photos. Essentially, any device that processes digital data generates digital signals. A key characteristic of digital signals is that they change in segments, and these changes are only between two fixed values, usually represented as 0 and 1. These two states are the foundation of digital communication and make the signals easy to interpret and process over time. Digital signals are used to represent physical quantities that change in segments, like sound, light, or temperature. By converting these physical changes into digital form, we can handle and manipulate the data more efficiently. One important point is that digital signals can be represented by just two values, 0 and 1. This binary nature is what makes digital signals so versatile and reliable. Because digital signals can be coded and compressed, the chances of losing data during transmission are significantly reduced. This is crucial for maintaining quality and integrity across communication channels. Digital signals are also stored easily in various storage devices, which is why we see digital TV, satellite TV, and dish TV all relying on digital signals to deliver content seamlessly. And finally, there are digital-to-analog converters. These devices transform digital signals back into analog signals. This process is vital in electronic devices like speakers, where sound needs to be converted back into analog form to be heard clearly. Overall, digital signals are fundamental to modern electronic communication, offering efficiency, reliability, and high-quality data transmission. Let's take a closer look at how digital signals are represented. In digital electronics, we often use a square wave to illustrate the digital signal. This shape is crucial because it clearly shows the binary states, either a high or a low. The square wave's sharp transitions between these states make it easy to distinguish between a 1 and a 0. This visual representation helps us understand how digital systems process and transmit information reliably. It ties into the overall theme of digital communication, highlighting how simple, binary signals form the backbone of modern electronic communication systems. Let's talk about signals and their types. Signals are basically the carriers of information, and understanding their different types is crucial for grasping how communication systems work. There are two main categories we focus on: analog signals and digital signals. Analog signals are continuous, meaning they can take on any value within a range, which makes them great for real-world data like sound and light. Digital signals, on the other hand, are discrete. They represent information through binary values, zeros and ones, which makes them more robust against noise and easier to process electronically. Recognizing these differences helps us choose the right signal type for specific applications, whether it's transmitting voice, data, or video. Connecting this to the overall theme, understanding signal types is fundamental because it influences how effectively information is transmitted, received, and interpreted in any communication system. Let's talk about storage capacity. At the most basic level, a bit is the smallest unit of computer memory. The word bit actually comes from binary digit, which makes sense because it can only represent two things. Think of it as a switch that can be either off or on, so either 0 or 1. This simple binary system is the foundation of all digital data. Now, when we combine bits, we can store more complex information. 4 bits make up a nibble, and 2 nibbles make a byte. Interestingly, 8 bits equal 1 byte. This is a crucial concept because bytes are what most computers use to store characters and other data. As data storage scales up, we move into larger units. For example, 1024 bytes make up 1 megabyte. Then, 1024 megabytes give us a gigabyte, and 1024 gigabytes make up a terabyte. These larger units are how we measure larger storage devices like hard drives and SSDs. Understanding these units is essential because it helps us grasp the capacity of storage devices and how much data we can save or process. It all starts with that tiny bit, but it quickly adds up to the massive storage capacities we're familiar with today. Now let's talk about signal transmission. Essentially, this is the process of sending and receiving signals from a transmitter to a receiver. It's a fundamental concept because it underpins how data and information flow across networks. There are two main types of signal transmission we need to understand: analog communication and digital communication. Analog communication involves continuous signals that vary smoothly over time, like traditional radio or television broadcasts. Digital communication, on the other hand, involves discrete signals. Think of how computers process data in binary form. Within digital communication, there's a further classification into two categories: baseband transmission and broadband transmission. Baseband transmission sends digital signals over a single channel without modulation, often used in local area networks. Broadband transmission, however, uses multiple channels or frequencies to transmit data simultaneously, which is typical in high-speed internet connections. Understanding these types is key because they directly influence how efficiently and effectively data travels, impacting everything from internet speeds to communication reliability. This ties back to the overall theme of how communication systems are designed to optimize signal transfer across different mediums and environments. Today, I'll be explaining the process of analog communication, which involves transferring data using analog signals from the transmitter to the receiver. This method is quite fundamental in communication systems. Now, let's look at some key features of analog communication. First, the signal is never converted into a digital form. It remains in its original analog state throughout the transmission. This means that the information is conveyed through continuous signals. Secondly, analog signals can be affected by external interference, such as noise from electrical devices or environmental factors, which can sometimes distort the message. Because of this, the signals are more vulnerable to disruptions compared to digital signals. Third, signals in analog communication cannot be coded in the same way digital data can be. This limits the flexibility in how we manipulate or secure the data during transmission. Fourth, analog communication generally uses low bandwidth, which means it requires less spectrum space, but also limits the amount of data transmitted at once. Fifth, when it comes to data processing, it's not always easy or straightforward with analog signals. The processes involved are often more complex and less precise. And finally, there is a higher chance of errors occurring during data processing due to the susceptibility of analog signals to noise and interference. Overall, while analog communication has its advantages, these features highlight some of its limitations, especially in modern, high-speed data transmission scenarios. Let's look at an example of analog signal transmission. When we think of a landline phone, it uses analog signals to transmit voice effectively. The process begins with the microphone, which receives the sound. Think of someone speaking into the phone. That sound is naturally an analog signal. Next, the microphone converts this sound into an electrical signal, which remains an analog signal. This electric signal is then sent through the phone line to the receiver. When it reaches the receiver, the speaker inside the phone converts the electrical signal back into sound, allowing us to hear the original voice clearly. What's important to note here is that the entire transmission happens without converting the signal into digital form. It stays analog from start to finish. That's why a landline call is a classic example of analog signal transmission. Similarly, traditional walkie-talkies used by police officers also rely on analog signals. They transmit voice directly as analog signals, which makes communication quick and straightforward in many situations. So, in essence, analog transmission involves passing continuous signals directly from sender to receiver, preserving the original sound or information throughout the process. This concept ties into our overall discussion on different types of communication signals and how they impact the way information is transmitted. Let's take a closer look at the components of analog communication. At the very start, we have the analog input, which is the original signal we want to transmit. This input is then captured by an input transducer, a device that converts the physical signal, like sound or light, into an electrical form. From there, the signal goes to the modulator, where it is prepared for transmission by altering its properties to suit the channel. Next, the modulated signal travels through the channel, which is the medium, such as a wire or air, over which the signal is sent. Upon reaching the receiver, the demodulator comes into play, extracting the original information from the transmitted signal. This is followed by the output transducer, which converts the electrical signal back into a physical form, like sound or light, that we can interpret. Finally, we get our output signal, which is essentially the original information reconstructed and ready for use. Understanding each step helps us see how analog signals are processed and transmitted efficiently, connecting the physical world with the communication system. Digital signal transmission, also known as digital communication, is all about sending information over physical media using digital signals. Essentially, instead of analog waves, we're working with discrete, binary data, zeros and ones, that can be easily processed and transmitted. When I say digital communication, I mean the process where data is transferred from a transmitter to a receiver, with digital signals acting as the messengers. This process is crucial because it ensures data integrity, speed, and efficiency in modern communication systems. Connecting this to the overall theme, understanding digital signal transmission helps us grasp how digital technologies enable the seamless exchange of information in our digital world. Let's take a closer look at the signal sender part of digital communication, specifically focusing on broadband signals. The process begins with the source, which generates the original information we want to transmit. From there, the signal passes through a filter to shape or select certain frequencies, ensuring the signal is suitable for transmission. Next, the filtered signal is converted from an analog form to a digital form using an ADC, or analog-to-digital converter. This step is crucial because digital signals are more robust and easier to process. After digitization, the signal undergoes coding, which involves compressing or encoding the data to optimize transmission efficiency and ensure error detection. Once coded, the digital signal moves to the transmitter, where it's combined with a modulator. The modulator is responsible for converting the digital data into a form suitable for transmission over the communication channel, often by varying carrier signals. Finally, the modulated signal is transmitted across the communication medium. This entire process is fundamental in digital communication systems because it ensures that information is accurately converted, encoded, and prepared for reliable transmission over broadband channels. Each step plays a vital role in maintaining the integrity and efficiency of the data as it travels from sender to receiver. Now, let's take a closer look at the signal receiver part of digital communication, specifically in the context of broadband systems. When a signal is transmitted, the receiver's first job is to capture that incoming signal through reception. Once received, the signal undergoes demodulation, which is essential for extracting the meaningful information from the carrier wave. After demodulation, the signal is processed by a decoder, which plays a crucial role in interpreting and converting the data into a usable form. Depending on the system's needs, this decoded data can then be converted into an analog signal using a digital-to-analog converter, or DAC, especially when analog output is required. Alternatively, if the system is designed for digital processing or digital interfaces, the output remains digital, ready to be sent to other digital systems or components. Understanding this chain, from reception through demodulation, decoding, and finally to either analog or digital output, is fundamental to grasping how broadband digital communication systems effectively transmit and receive data. This process ensures that the information arrives accurately and in the right format for subsequent use. Let's take a closer look at the key features of digital communication. First, the data is converted into a digital signal at least once during transmission. This means that information is transformed from its original form into a series of digital bits, which makes the data easier to manage and process. Second, digital signals are not affected by external interference. Unlike analog signals, which can be distorted by noise or other external factors, digital signals maintain their integrity much better, ensuring more reliable communication. Third, signals in digital communication can be coded. Coding allows us to add error detection and correction features, which helps in maintaining data accuracy throughout the transmission process. Fourth, digital communication uses high bandwidth. This means it can carry a large amount of data quickly, supporting faster and more efficient communication channels. Fifth, data processing becomes easier in digital systems. Since data is in a standardized digital format, it simplifies tasks like editing, storage, and analysis. Lastly, there's less chance of errors during data processing. Digital systems have built-in error detection mechanisms, so the likelihood of mistakes is significantly reduced. Overall, these features highlight how digital communication offers a more robust, efficient, and reliable way of transmitting data, which is central to the modern digital world we live in. Let's take a closer look at how digital signal transmission works in mobile phones. When you speak into the microphone, it first captures sound energy. That's your voice. This sound is then converted into electrical signals, which are analog in nature. To efficiently transmit these signals, the phone uses an analog-to-digital converter to transform the analog signals into digital signals. These digital signals are more robust and easier to process, especially over long distances. Once converted, the digital data is turned into radio waves, which travel through the air to reach the cellular network. On the receiving end, a demodulator picks up these radio waves and extracts the digital signals. Then, a decoder processes these signals to ensure they're correctly interpreted. Finally, the digital-to-analog converter converts the digital data back into an analog signal, similar to the original sound, so that you can hear your voice clearly through the speaker. This entire process illustrates how digital technology enables clear, efficient voice communication in mobile phones, connecting all the parts of the transmission cycle seamlessly. Let's take a closer look at signal transmission and its types. When we talk about signal transmission, we're essentially discussing how information travels from one point to another in a communication system. This is a fundamental aspect because the effectiveness of any communication depends on how well these signals are transmitted. There are two main types of signal transmission: analog and digital. Analog transmission involves continuous signals that vary smoothly over time, much like a traditional radio broadcast. Digital transmission, on the other hand, uses discrete signals. Think of binary data, zeros and ones, which are more robust against noise and interference. Understanding these types helps us appreciate the design choices in communication networks and how they impact speed, quality, and reliability. Connecting this to the overall theme, effective signal transmission is at the heart of reliable communication systems, enabling us to transmit data efficiently across various platforms. Now, let's take a closer look at baseband transmission. Essentially, this is a type of digital transmission where the digital signal is sent directly from the sender to the receiver. What's important here is that the signal remains in its digital form throughout the entire process. Unlike other methods, the digital signal isn't converted into an analog signal at any point during transmission. This direct approach simplifies the process and is often used for local area networks and digital communications, reinforcing the overall theme of efficient and straightforward data transfer. So let's take a closer look at baseband transmission channels. Essentially, this process starts with the sender's ICT tool, which is responsible for generating the digital data that needs to be transmitted. From there, this digital data is fed into an encoder, which converts it into a digital signal suitable for transmission. Once encoded, the digital signal travels through the channel, and then it reaches the decoder, which interprets the incoming digital signal back into a form that can be understood and utilized by the receiver. After decoding, the digital signal is delivered to the receiver's ICT tool, completing the transmission process. The key concept here is the entire chain from digital data creation to delivery, highlighting how each component plays a crucial role in ensuring accurate and efficient communication over the channel. This flow underscores the importance of encoding and decoding in maintaining data integrity and effective transmission, which ties back to our overall focus on reliable ICT communication systems. Let's take a closer look at the features of baseband transmission. First, one key point is that data is never converted into an analog signal. Instead, it stays in digital form throughout the transmission process. This is important because it simplifies the transmission process and helps maintain data integrity. Next, compared to broadband, baseband signals are sent at a lower frequency. This means it's suitable for specific applications where high frequency isn't necessary, particularly for short distances. Speaking of which, baseband transmission is mostly used for short-distance communication, such as within a local network or between close devices. Another important aspect is that the signal is transferred and received through the same channel, which means there's only one channel involved. This simplifies the design, but also limits the transmission distance. Now, looking at the advantages, baseband transmission is cheaper and easier to use. It doesn't require complex equipment or high costs, making it accessible for many applications. However, the main disadvantage is that it's only effective over short distances. Beyond that, the signal may weaken or degrade, limiting its usefulness for long-range communication. Connecting these points to the overall theme, understanding the features of baseband transmission helps us see why it's ideal for certain scenarios. Simple, cost-effective, short-range communication, while also recognizing its limitations. So let's look at an example of baseband transmission. Imagine you have two desktop computers or laptops, and you connect them directly using an Ethernet cable. When you transfer data this way, that's a perfect example of baseband transmission. It's a straightforward wired connection where the data travels over a single channel without any modulation or complex encoding. Similarly, if you connect a mobile device to a computer using a data cable to transfer files, that also exemplifies baseband transmission. In both cases, the data is sent directly over a dedicated medium, which is a key characteristic of baseband communication. This type of transmission is fundamental because it's simple, efficient, and often used for direct device-to-device communication, especially in local environments. It's a great illustration of how baseband transmission works in everyday technology, connecting devices directly and reliably. Now, let's talk about broadband transmission. Essentially, broadband transmission is a type of digital communication where digital data from the sender is converted into an analog signal for transmission. Once this analog signal reaches the receiver, it's converted back into digital data. This process involves converting digital signals to analog, transmitting them over the network, and then converting them back into digital on the other side. It's a continuous cycle that allows us to send large amounts of data quickly and efficiently. Some common examples of broadband transmission include sending emails, chatting on Messenger, sharing photos on Viber, making audio and video calls, and various forms of digital telecommunication. All of these activities rely on high-speed internet, which is what makes broadband so essential in our connected world. In essence, broadband enables us to access and share information rapidly, supporting the high-speed internet we depend on daily. Now, let's take a closer look at the broadband transmission channel. This is a critical component because it's the medium through which our data travels from the sender to the receiver. Think of it as the highway for digital information. The key points here are that broadband channels are capable of transmitting large amounts of data at high speeds, which is essential for modern applications like streaming, video conferencing, and cloud computing. It's important to understand that the quality and capacity of this channel directly impact the overall performance of the network. Factors such as bandwidth, noise, and signal attenuation can influence how effectively data is transmitted. Connecting this to our overall theme, the broadband transmission channel is what enables the high-speed, reliable connectivity we aim to achieve in our networks. Without a robust channel, even the most advanced technologies can't deliver the performance we need. So, optimizing these channels is fundamental to ensuring that our communication systems meet the demands of today's digital world. Let's take a closer look at the features of broadband transmissions. First, they use two different channels, meaning there are separate cables for sending and receiving signals. This separation helps improve the efficiency and clarity of communication. Next, broadband transmits signals at a much higher frequency compared to baseband transmission. This high frequency allows for greater data capacity and faster speeds. Another key point is that broadband requires modulation, which is a process that helps encode the signals onto higher frequencies for transmission. Because of this modulation, signals can also be coded, adding an extra layer of security and error detection. Additionally, broadband transmissions tend to have less crosstalk, meaning there's less interference between channels, which results in clearer signals. Lastly, data in broadband is transferred as an analog signal from the channel, which differs from digital transmission methods. All these features collectively make broadband a powerful and reliable method for high-speed data transmission, aligning with our overall goal of understanding efficient communication systems. Let's take a closer look at the advantages and disadvantages of broadband transmission. One of its key benefits is that it can be used for long-distance transmission. This means data can travel across vast areas without losing quality, which is essential for modern communication networks. However, on the flip side, broadband transmission also has some challenges. Its construction is quite complex and difficult, requiring advanced technology and precise setup. Additionally, the installation costs tend to be high, which can be a significant factor for organizations or governments considering this option. Understanding these pros and cons helps us evaluate how broadband fits into the overall network infrastructure and its role in supporting high-speed, reliable communication over large distances. Let's talk about digital signal transmission and its types. When we refer to digital signals, we're talking about signals that use discrete values, usually represented as binary zeros and ones. This is different from analog signals, which are continuous. Digital transmission offers several advantages, including higher noise immunity and easier processing. Now, there are primarily two types of digital transmission: serial and parallel. In serial transmission, bits are sent sequentially, one after another, over a single channel. It's commonly used for long-distance communication because it reduces the complexity and cost. Parallel transmission, on the other hand, sends multiple bits simultaneously across multiple channels. This method is typically used for short distances, like inside a computer, because it allows faster data transfer. Understanding these types helps us see how digital signals are efficiently transmitted in various systems, which is a key part of the broader topic of digital communication technologies. Let's walk through this signal flow to understand how analog signals are converted and processed. It all starts with the source, which is our original analog signal. This could be anything like sound, temperature, or other real-world data. To work with this signal digitally, we use an analog-to-digital converter, or ADC. The ADC samples the analog signal at specific intervals and converts these samples into digital data that a computer or digital system can understand. Once we have the digital signal, it can be processed, stored, or manipulated in various ways. After processing, if we need to output the signal back into the real world as an analog signal, we use a digital-to-analog converter, or DAC. The DAC takes the digital data and reconstructs it into a continuous analog waveform. Finally, this output signal can be sent to speakers, actuators, or other devices that operate with analog signals. This entire process, from the original analog source, through digitization, processing, and back to analog output, illustrates the core concept of how modern systems handle real-world signals efficiently and flexibly. This flow is fundamental to understanding how digital systems interface with the physical environment. Let's take a closer look at the components of digital transmission, specifically focusing on broadband. When we talk about broadband, we're essentially referring to high-capacity channels that can carry large amounts of data simultaneously. This is what makes broadband so essential for modern communication. It's capable of supporting everything from streaming videos to large data transfers. One of the key components here is the transmission medium, which can be fiber optic cables, coaxial cables, or even wireless channels. Each of these has its advantages in terms of speed and reliability. Fiber optic cables, for example, are known for their incredible bandwidth and low signal loss, making them ideal for high-speed broadband services. Next, we have the modulation techniques used to encode digital data onto physical signals. Techniques like QAM or quadrature amplitude modulation allow us to efficiently pack more bits into each signal, increasing the data rate without requiring additional bandwidth. Then there are the multiplexing methods, such as frequency division multiplexing, or FDM, which enable multiple signals to share the same transmission medium without interference. This is crucial in broadband systems to maximize the use of available bandwidth. Finally, we can't forget about error detection and correction mechanisms. These are vital to ensure that the data received is accurate, especially when transmitting over noisy or long-distance channels. Techniques like CRC or cyclic redundancy check help identify errors so they can be corrected or retransmitted. All these components work together seamlessly to provide the high-speed, reliable digital transmission that underpins our broadband services today. Understanding these elements helps us appreciate the complexity and sophistication behind the internet and digital communication as a whole. Let's walk through the key components involved in signal transmission. First, we have the source, which produces an analog signal that needs to be transmitted. This analog signal is received by the input transducer, which converts it into electrical signals. Once we have the electrical signals, an analog-to-digital converter, or ADC, steps in to turn those signals into digital form, making them easier to process and transmit. Next, we have the encoder. The encoder's job is to compress this digital data into the smallest possible number of bits, ensuring efficient use of bandwidth. Then comes the modulator, which amplifies and modulates the signal, adding a carrier signal that makes it suitable for transmission over the channel. After modulation, a digital-to-analog converter, or DAC, converts the signal back into an analog form, preparing it for transmission. The signal then travels through the channel, which is essentially the path it takes to reach the receiver. The channel can be a wire, fiber optic cable, or wireless medium. Once the signal reaches the channel, it makes its way to the receiver, completing the transmission process. Throughout this entire process, each component plays a crucial role in ensuring that the original message is accurately transmitted and received. This sequence highlights how signals are transformed and prepared for effective communication across various media. Now, let's look at the demodulator, which is a crucial part of the receiver. Its main job is to separate the original signal from the carrier signal. Think of it as the filter that extracts the useful information we want to recover. It's the very first stage on the receiver side, setting the foundation for everything that follows. Next, we have the decoder. Once the signal is demodulated, it's often encoded to protect against errors during transmission. The decoder takes this encoded signal and converts it back into a usable form. It also plays a key role in reducing errors, ensuring the data we receive is as accurate as possible. This step is vital for maintaining high-quality communication, especially over long distances. After decoding, the signal is still in digital form, but we need to convert it back into a format that humans can understand, an analog signal. That's where the output transducer comes in. It changes the digital signals into the original analog signals, like sound or video, so we can actually interpret what's been transmitted. Finally, the output transducer produces what we call the output signal. This is the final, processed signal that we receive and can interact with, whether it's audio, video, or any other form of information. Together, these components form the backbone of the receiver, transforming the raw signals sent over the airwaves into meaningful information that we can use. Let's talk about the effect of digital technology. As we integrate more digital tools into our daily lives, we see significant changes across various sectors. For one, digital technology has revolutionized communication, making it faster and more accessible than ever before. We can connect instantly with people around the world, breaking down geographical barriers. It has also transformed industries like education, healthcare, and commerce, enabling more efficient processes and better access to services. However, with these benefits come challenges, such as data privacy concerns and the digital divide, which can create inequalities. Overall, digital technology acts as a catalyst for innovation and progress, but it's important to manage its impacts thoughtfully. Recognizing these effects helps us leverage technology in ways that enhance our lives while addressing potential risks. Let's take a moment to look at the role of information and communication technology, or ICT, and some key terms associated with it. ICT is essentially the backbone of modern communication, enabling us to connect, share, and access information instantly across the globe. When we talk about key terms in this area, we're referring to concepts like bandwidth, which determines how much data can be transmitted at once, latency, or the delay before a transfer of data begins following an instruction, and protocols, which are the rules that govern how data is transmitted and received. Understanding these terms is crucial because they directly impact the efficiency and effectiveness of our communication systems. As we explore these concepts, keep in mind how they tie into the broader theme of digital transformation and innovation. These technologies are not just tools, they are fundamental to how organizations operate and compete in today's digital age. Let's talk about digital well-being and online reputation. These are crucial aspects of our digital lives that can often be overlooked. Digital well-being is all about maintaining a healthy balance between our online activities and our offline lives. It involves being mindful of how much time we spend online and the impact it has on our mental health and overall well-being. On the other hand, our online reputation is what others perceive about us based on our digital footprint. This includes social media profiles, posts, comments, and even the information that appears in search results. It's important because it can influence personal relationships, career opportunities, and how we are viewed by the wider community. Both concepts are interconnected. When we manage our digital well-being effectively, we're also more likely to curate a positive online reputation. Being intentional about what we share and how we engage online helps us protect our reputation and foster a healthier digital environment. Remember, in today's digital world, maintaining a good balance and being conscious of our online presence isn't just beneficial. It's essential for our overall personal and professional growth. Let's talk about audio-video editing. This is a crucial step that really brings your content to life. When we're editing audio and video, the goal is to enhance clarity, engagement, and overall quality. It's about trimming out any unnecessary parts, adding transitions, or effects that make the flow smoother and more professional. Highlighting the key points, remember that good editing can improve storytelling, making your message more impactful. It also helps maintain the viewer's interest and ensures your content looks polished. Think of it as the finishing touch that connects all the elements seamlessly. Connecting this to the overall theme, effective editing is what transforms raw footage into a compelling final product. It's where your creative vision really comes through, making sure your message resonates with your audience. So, mastering audio-video editing is essential for producing professional, engaging content that truly stands out. Let's walk through the process of signal conversion in antenna television. First, an incident wave, which is the electromagnetic signal traveling through the air, is captured by the tag antenna. This antenna acts like a receiver, picking up the broadcast signal. Next, the signal is sent to a transistor, which amplifies or processes it further. From there, the signal undergoes modulation to become an analog signal, meaning it varies continuously to carry the information. Finally, this analog signal is converted into a digital signal, making it easier to process, store, and transmit with modern digital systems. This entire chain, from incident wave to digital signal, illustrates how TV signals are transformed from their initial broadcast form into the digital data that our devices can understand and display. Understanding this process is key to appreciating how television technology has evolved to deliver clearer, more reliable images and sound. Now, let's explore the different types of modulation that are commonly used in communication systems. First, we have frequency modulation, which is also known as frequency shift keying, or FSK. In FSK, the frequency of the carrier wave is varied in accordance with the digital signal, allowing us to encode information through changes in frequency. This method is quite robust and widely used in radio transmissions. Next, there's amplitude modulation, or ASK, where the amplitude of the carrier wave is adjusted to represent data. Think of it as turning the strength of the signal up and down to convey information. ASK is simple to implement, but can be more susceptible to noise, making it suitable for certain applications. Finally, we have phase modulation, called phase shift keying, or PSK. In PSK, the phase of the carrier wave is shifted to encode data. This technique is very efficient because it can transmit more bits per symbol, which makes it popular in digital communication systems like Wi-Fi and Bluetooth. Connecting these to our overall theme, understanding these modulation types helps us grasp how digital information is reliably transmitted over various channels, each with its own advantages and trade-offs. Now let's talk about video file formats. Common ones include MP4, 3GP, SVI, and MOV. Each of these formats has its own strengths and is compatible with different devices and software. When you're working with videos, it's important to choose the right format for your needs. Next, to edit your videos, you'll open your video editor. Then, navigate to the library or media section to add your video files. Once your files are loaded, you can mark the initial and final positions, basically selecting the part of the video you want to keep or modify. After selecting the segment, simply press the Cut button. This allows you to trim or remove unwanted sections. Once you're satisfied with your edits, click Export to render the final version. Finally, save your edited video to your preferred location. These steps are essential for creating polished, professional videos that support your overall presentation or project. Thank you all for your time and attention today. I genuinely appreciate your engagement and interest in this topic. Remember, the key takeaways from this presentation highlight the importance of understanding the core concepts we've discussed and how they apply to real-world scenarios. I hope you found the information valuable and that it inspires you to take action or explore further. If you have any questions or want to discuss anything in more detail, please don't hesitate to reach out. Once again, thank you so much for being here and for your participation.